All right, Chicos, here we go. We are looking at dividing radicals. I want you to be able to do that when you walk out of here. Let's give it a shot. All right, let me show you a neat trick that'll kind of be the foundation for all of this. If you take root 100 and divide by root 4, you can evaluate the numerator and denominator first. You get 10, you get 2. When you divide, you get 5. You can look at the same sort of setup, but with the division under the radical. You do the division first, so you do 100 divided by 4, that's 25, and then take the square root and you get the same result. Now this isn't a proof, but it shows this quotient property of radicals in that if you have a division under the radical, you can break that into a radical in the division. So you make it, instead of root a over b, you make it root a over root b. So we're going to use that to our advantage. All right, so we're going to use that idea here. You'd use it like this, root 12 over root 6. I don't know, those are nasty decimals. But if you put them under one radical instead of separate radicals, you can simplify that to root 2 and just leave it, right? This would simplify to root 2 if you put it in your calculator. If you did the same thing here, maybe you want to pause me and try it. You could take this and take the root of the numerator and denominator first, or you could simplify the inside and make it root 7/4. I'm just simplifying the fraction first. And then take the radicals of the numerator and denominator and simplify that denominator. Root 4 is just 2, right? Then you can leave it. What's nice about that is if you had something like, if this was really 4 times this mess, if it was 4 times all of that mess, then you'd have 4 times root 7 over 2. This is sort of like 4 over 1 times root 7 over 2. And when you multiply them, the 4 and the 2 cancel out. Oh, that's a 7, sorry. And then you'd be left with 2 root 7. That's why we like to do that. All right. This is why we rationalize the denominator. This whole idea of rationalizing the denominator is to make a whole number in the bottom. And here's why. It makes sense when you're dividing. If you take 1.5 pizzas and you divide them amongst 2 people, that's fine. You can take like a fraction of pizza and divide them among 2 people. Look, everybody gets 1 for you, 1, 2 for you, 2 for you, 3 for you, 3 for you. That makes sense. But 2 pizzas, those are 2 whole pizzas, divided by 1.5 people. What does this guy, his torso fell off, and now you're dividing the 2 pizzas among 1.5 people. This doesn't make sense, and it's gross. So we don't like having this decimal in the denominator. So when you have something like 2 divided by root, out of there. So what we end up doing is rationalizing the denominator, and that's this step. Here's an example of one, but what we're going to do is take the denominator and multiply by that fraction by another fraction, which is the denominator in the numerator and denominator. So we're going to take the 6 over root 3 and multiply by this over itself. And what that's going to do for us is give us a root 3 times root 3 is root 9, and root 9 is 3, and now our denominator is at least a whole number. Maybe it'll cancel out, right? 6 divided by 3 is this 2, and this root 3 is still there, 6 divided by 3. And so that's a lot nicer. Yeah. Try this out on your own. Maybe instead of 16 over root 5, let's call it 15 over root 5. I think it'll yield more satisfying results. So maybe instead of 16, call it 15. And play the same game. You can pause me if you like. Maybe let's call it root 5, or let's multiply by root 5 over root 5. This is 1, right? Anything divided by itself is 1, so we're not changing the essence of the fraction. But when we do that, you're left with 15 times root 5, that's ugly, over root 5 times root 5 is root 5 squared, which is just 5, or it's root 25, which is 5 also, doesn't matter. And so these can simplify to 3. So you end up with, as we started, it would end up with 16 root 5 over 5, and it's not particularly satisfying, just because. All right, you try these out. I think we've done this one, but we'd multiply numerator and denominator by root 3 over 3, root 3. Those give you root 9, which is 3 in the denominator. The 6 and the 3 cancel out, and you're just left with a 2, root 3. Likewise, here, we'd multiply by a fraction that's root 7 over root 7. This is 1, so we're not changing anything. When you multiply everything on top, you get 35 root 7. Oh. When you multiply everything on bottom, you get root 49, which is just 7. And then your 5 and a 7 from the 35 and a 7 from the 7 cancel out. Okay, so once in a while you get a denominator that doesn't just have a radical in it, but an addition in it. And you need to multiply by not just the radical, but the conjugate, which means the same thing but switched signs. So that and that are different. So for example, this, you'd multiply top and bottom by the denominator with the sign switch. That's called the conjugate. And when you do that, you get the 5 times the root 3 and the 5 times the root, 5 times the 3 and the 5 times the root 2, which is fine. And you also multiply the denominators together. You get the 3 and the 3 give you this 9, and you get the root 2 and root 2 give you just 2 and negative. And the 3 and root 2, and this is exactly the same but negative. Negative 2 and 3, they cancel out, that's why you don't see them there. And then you can simplify the numerator into 15 and 5 root 2. This is 9, this is negative 2, this is 7. Try that here. Here's an example. If you want to check that out, try it with this. I would multiply by 7 minus root 3 over 7 minus root 3. That's when you multiply 4 into this numerator, you end up with 4 times 7, which is the 28, minus 4 root 3s. That's all fine and dandy. I'm going to put some parentheses around the denominators, and when you multiply these, you end up with 49. When you multiply, running out of colors, these, you end up with negative 7 root 3s. That's positive, that's negative, so it'll be negative, and 7 times root 3 is 7 root 3. And when you multiply this times this, they're both positive, so you end up with 7 root 3. And when you multiply the root 3 times the negative root 3, you end up with negative root 9, which is just 3. These two are the same value but opposite signs, so they cancel out. And you're left with the numerator, 28 minus 4 root 3, over 46. It looks ugly still. It doesn't look particularly nice, but it's nicer than having a fraction or a decimal in the denominator. So we say that's simplified. This is the same idea, but they're saying let A, leave it in this format, and A and B are in the set of rational numbers, so it means they can be fractions. So we do the same thing, multiply numerator and denominator by the conjugate, and when you simplify that, you get just this numerator in the top, and you get 25 from the 5s, you get 2 from the negative 2 from the root 2s, and the 5 root 2 and the other 5 root 2 have opposite signs, they cancel. I hope you're good there. I hope that's kind of what we did before. They said leave it like this, which has no fraction, so you can break it into this fraction minus that fraction, right? 1 over 23. Not ideal, but whatever. It's better than, it's in the form that they asked for. If you are comfortable getting here, I'm really happy. Cool. Hope you're doing well. We're going to do 5F1, 5F2 for home learning. See you later.